Okay, so what we're going to do now is, as we're jumping into General Chemistry 2, we're going to review some of the important concepts from the first semester of General Chemistry 1, just so that we can, make sure that we're starting off on a solid foundation. So there are several things, several main concepts that we need to make sure that we have a pretty good grasp of in order to understand and to efficiently navigate the General Chemistry 2 content. So the first thing we're going to start with are kind of central to chemistry in general, and those are chemical reactions. Okay, so what we're going to be taking a look at here is just to quickly remind ourselves what chemical reactions are, um, how they are arranged, different types of reactions, etc. So chemical reactions are nothing more than chemical sentences, if you will. Okay, and I often abbreviate reactions as RXN. That's a very common abbreviation for the word reaction. Um, and well, let's back up a sec here. So a chemical reaction chemical reactions are chemical changes. Okay. And as we know, chemical changes are changes where we change the makeup of something from, what we start with, and we change how the atoms are arranged. We end up with something very different at the end, right? So the identity of the material changes in a chemical change, and that's different than in a physical change where the identity of the substance stays the same. So these chemical reactions or chemical changes are shown as chemical equations. And that's what we're going to focus on here is the chemical equations. And I abbreviate equations as EQN. And these are the chemical sentences. Okay, we'll put sentences in quotation. They're not a typical, English sentence, for example. These are chemical sentences that represent chemical changes or chemical reactions. So very, very simply, let's take a look at a couple examples, and I'll pick one chemical reaction and kind of use that as our template for a lot of what we're going to use to review these. Okay, so let's say that we have the following chemical equation. So we have N2 plus H2 to give NH3, and then we have these other things that are thrown in here. And then we have some other things that are thrown in here as well. Okay, so this is what a typical chemical equation is going to look like. And it represents the reaction for the production of ammonia, which is NH3 over on the right side, when we react nitrogen and hydrogen together. Okay, so first thing that we need to remember from chemical equations is there's this arrow here in the middle that always points from the left to right by default. On the left side of the arrow, we have what are called our reactants, are on the left side. And then we have the product or products, if we have multiple, that are on the right side of the equation. Okay, so reactants on the left, if we have multiple reactants, we separate them with a plus sign. That just means that we have multiple. And then on the right side, we have our products. So reactants react together to produce products on the right. A couple things here that you will note. These symbols, these abbreviations that are in parentheses, these are known as state symbols, and they represent the physical state of the reactants and products. Okay, and there are four of these that we're going to see. G represents a gas, L represents a liquid, S represents a solid, and then the other abbreviation state symbol that we'll see is AQ, and that's represent an aqueous solution, and that typically means that that substance is just dissolved in water. Okay, so that's the anatomy of our chemical equation. Reactants on the left react to produce products on the right side of the equation. And then we use our state symbols to tell us what the physical states of the reactant and products are. The other thing that you will see here is that these numbers that are inserted in front of the chemical formula for the reactant and products. So these are known as coefficients. Okay, and they are there. We use them to balance the equation. And the reason why we want to do that is so that we adhere to the law of conservation of matter. Okay, and the idea behind that is that whatever things you start with should be the same things that you end with. So if I start with two nitrogens, I should end up with two nitrogens. If I start with three hydrogens, I should end up with three hydrogens. Now, they may be separated from each other when they in the reactant side, but when we recombine them, they may be combined together on the product side, and that's the point of chemical changes, right? We change the makeup of the substances, but the actual components, the atoms themselves, the nitrogens and the hydrogens, they don't change, right? It's just the way that we connect them is what changes. That gives us those different products on the right side. So we use those coefficients. If you don't see a coefficient, so like in the case in the front of N2, if you don't see a coefficient in front, 1 is understood to be there. We don't usually write the 1 in, but it is there. What you don't want to do is put a 0. That means there's nothing there. Okay, so that's typically how all of the reactions are going to look. This is a fairly simple one, but whether it's something more complicated or there are, 4 or 5 reactants and 6 or 7 products, it doesn't really matter. They're all going to look the same way. Okay, so that's your general layout of a chemical equation, which is what is used to represent your chemical change or your chemical reaction. Okay, so the next thing that we're going to do is take a quick look at how we balance equations. And again, the idea behind balancing equations is so that we don't violate the law of conservation of mass or the law of conservation of matter. And the only thing that we can do to balance our equations is we're going to use these coefficients, right? So we're going to insert coefficients, which are just simply, this is just a fancy word for a small whole number, in front of the chemical formulas. Okay, that's the only thing that you can do to balance an equation. You cannot change the formula of something. You cannot insert numbers within a formula. So what I like to do is I like to put a line in front of the chemical formulas so that way I know exactly where those coefficients are going to go. And when it comes to balancing equation, there are little tricks and little strategies you can use to help you balance your equations more efficiently. Really what it just boils down to is just trial and error, but it's not just a random thing. You can actually use some strategies to make the balancing go by a little bit smoother. So what I like to start off with is to list the atoms that I have on the left side and the right side. And you should have the same, right? Because we can't change the atoms into different atoms. So if I start listing, I have sodium, Na, I have Cl, I have Al, aluminum. And then what you'll notice here is I have in the nitrate, which is the NO3, I have nitrogen and I have oxygen. So you may be tempted to write the N and then the O. But you should be able, and you should remember that NO3 is nitrate. That's a polyatomic ion. And one of the strategies is if you see the nitrate here on the left and you see the nitrate on the right, what you can actually do is you can try to balance the nitrates as a collection, so NO3, instead of breaking it down into the N's and the O's. Now you could do that, obviously. You can have your N and your O's. It'll just take you a little bit longer, but you should get the same answer. And next thing we're going to do is just look at the subscripts that tell us how many of each of these atoms that we have. So you don't see a subscript and one is understood. So I have one Na, I have one Cl, I have one aluminum, and now the nitrate, I have 3 NO3s, right? So I'm going to put that there. Remember, when you have a parentheses and a subscript outside of it, 3, whatever that subscript is, gets applied to that entire thing in the parentheses. On the right side, I have 1 sodium. Now I have my nitrate here. I'm going to put parentheses around it just so that it's easier to see. And I have 1 of those, so 1 nitrate. I have 1 aluminum, and I have 3 Cls. Okay, so by initial inspection, I can see that the sodiums are already balanced, the aluminums are balanced, but the chlorines and the nitrates are not. So let's try to balance each of these things. So let's start with the chlorines first. So I have three chlorines here on the right side. I need to make three chlorines here on the left. Okay, what you cannot do is put a 3 as a subscript, right? That's changing the formula, and you can't do that. So to make three chlorines, I'm going to have to put the 3 as a coefficient in front of the thing with the chlorine. So this now gives me 3 Cls. Okay, but now I've also changed my sodiums to 3. So I need to keep track of that. Now I put the sodium out of balance. Let's go ahead and balance the sodiums on the right side. So right now I've got 1 sodium here. I need to make 3. So I'm going to put a 3 in front of the thing with the sodium. So I make 3 sodium. But now I've also changed my nitrates, okay, to 3 nitrates. And by doing that, guess what? I've now automatically balanced my nitrates that I had at the beginning. I didn't mess with the aluminum, so the aluminum is still good. So I can put the 1 in front if that makes you feel better, but it's not necessary. So 1 aluminum and then 1 times 3, which is the 3 nitrates, which is already balanced. This is good, that's good, sodium's good, nitrate's good. So this is going to be your balanced equation for this particular reaction. Okay, so you need to be fairly proficient at doing this. And efficient as well, meaning you need to balance equations fairly quickly. All right, next I'm going to take a look at are the different types of equations, types of reactions as well. And there are 5 main types that you may have seen before. And we're going to take a look at some other types of reactions a little bit later on in General Chemistry 2. So let's just quickly review the 5 main types you've seen previously. So the first one is called combination, or sometimes it's called synthesis. Okay, so in a combination or a synthesis reaction, what we have is multiple, meaning more than one reactants combined together to produce one type of product. Okay, so in all of the examples that I'm going to take a look at and kind of use to show you, I'm not going to balance the equations. That's not the point of this section. It's just to show you the different types. Okay, and we already just actually looked at one example of a combination or a synthesis, which is the nitrogen combining with hydrogen to produce ammonia, NH3. All right, so I have my one type of a reaction, and I have multiple, okay, more than one, multiple meaning more than one reactant. So that's a combination or a synthesis. Now, the opposite of this is called a decomposition. Okay, and as the name sort of suggests, in a decomposition reaction, we're going to start off with one type of reactant. So one thing on the left side is going to break down or decompose to produce multiple products. Okay, so you're going to have more than one thing on the right side. And if you take this reaction, the one that we had originally, and we just reversed it, that would be a decomposition. So if I have my ammonia and I broke it down into its components, nitrogen and hydrogen, that would be a decomposition reaction, right? So combination and decomposition, just opposite or reverse processes. The third type is called a single replacement. Sometimes this is called a substitution reaction. Okay, and in a single replacement or a substitution reaction, we have one element that takes the place or substitutes another in a compound. So substitutes another element from a compound. So for example, I'll give you 2 examples of these. If we have zinc, Zn, and hydrochloric acid, HCl, what can happen here is the zinc can come in and it can kick the hydrogen out. So it takes the place of the H. And hydrogen here is going to be kicked out as hydrogen. Hydrogen occurs naturally as a diatomic. So it's H2, and that's a gas. And then when the zinc takes the place of the hydrogen, now we need to make a new combination, right? So we're going to get our zinc and the chloride, and that would be zinc chloride, which has the formula ZnCl2. Okay, so what we end up doing here, essentially, we have an element and a compound. Okay, the element takes the place of one of the elements from that compound. So we end up with a new element, meaning by itself. And we get a new combination, which is our new compound. Okay, so that's a single replacement or a substitution. So the zinc substitutes or replaces the hydrogen. So typically, in this case, we have a metal that replaces hydrogen, or sometimes you'll have a metal that replaces another metal from a compound. If we take this one step further, we have what's called a double replacement, or sometimes this is known as a metathesis. Okay, and then here what we have is two elements that swap places in their compounds. And then as a result, we're going to produce two new compounds. Okay, and the example that we did previously up here is a good example of one of those double replacement reactions. So let's just revisit that. We had our sodium and we had our aluminum nitrate. Okay, so what's happening here? We have two elements, and in this case, there are two metals that are going to swap places. So the sodium comes in and kicks out and takes the place of the aluminum. And guess what? The aluminum is going to go and it is going to take the place of the sodium, right? So they're essentially just swapping locations. And then when you now combine those, when you make those two new combinations, you have to make sure that they combine in the correct ratio, right? So you need to come up with the correct formulas, which means you need to know the charges that these ions will have, and then you need to combine them in the correct ratio so that those charges cancel out. Right? So for example, aluminum being in group 3 will form a 3+ charge. So when the aluminum and chlorine, when they combine, chlorine is in group 7, so it'll form a -1 charge. That's why we need 3 chlorines or chlorides for every aluminum, because each chloride is 1 minus. We need 3 of them to give us 3 minus to cancel out the 3+ from the aluminum. So once we have our first compound predicted, we can then do the other combination. So sodium, so we have our Na is going to combine with the nitrate. So Na is in group 1. It'll form a +1 charge. And then nitrate is one of those polyatomic ions, has a -1 charge. So the +1 -1 will cancel. So these combine in a 1-to-1 ratio, right? So we have NaNO3, sodium nitrate, as our other compound. This is a double replacement, two elements swapping places to make two new compounds. The last one here we'll take a look at is called a combustion reaction. And in a combustion reaction, typically what we have is typically we'll see a carbon-containing compound reacts with oxygen. So O2 gas to produce carbon dioxide, CO2, and water vapor, H2O. And then this is for complete combustion, because we can also have incomplete combustion. So this is assuming that there's lots of oxygen present. Okay, and this is a reaction, combustion reaction, the reactions that happen all the time, from the gasoline in your car to the foods that you eat, they all undergo combustion reactions. And the goal of that is to produce not just the CO2 and H2O, but you also get a bunch of energy from this as well. And that's the main goal of these combustion reactions. So for example, if we have something like in your gasoline, you have something called octane, which is C8H, that should be 18. And by the way, at the end of this semester, you will do a little project on organic compounds. You'll see octane. This can react with oxygen. So complete combustion, we're going to get CO2. So we know what the products are going to be because I just told you what they are. And we're going to get H2O. And then you obviously need to balance this reaction, which may take several steps. But the point here is you have a carbon-containing compound reacting with oxygen. And for complete combustion, we're going to get CO2 and H2O. If we have incomplete combustion, which does happen. So for example, you don't want to have your car running in a closed garage because there's not enough air and by extension oxygen for that fuel to completely burn. So as a result, you're going to get incomplete combustion. And when you have that, we also produce, in addition to the CO2 and H2O, it also produces CO, which is carbon monoxide, and that is highly poisonous, right? Small amounts of that can actually kill you, which is why you don't want to have a grill, for example. You have your grill when you're grilling, barbecue, whatever. You want to do that outside. You don't do it inside your house because you want that fuel to burn completely. Same thing with your cars. You don't want them running in a closed garage if they are normal, internal combustion engines. All right, so those are the 5 main types of reactions. And we have our equations that represent those reactions that we need to remember and refamiliarize ourselves with. If this sounds a little foreign to you, you need to make sure and spend the extra time reviewing this.